Hey guys, this is Einar. I hope that you're doing great today and welcome to this tutorial where we are going to be talking about ordinary least squares or OLS linear regression. My name is Einar Stenson and I work at the Department of Sociology at the Stockholm University. This is my email address and you can always contact me if you have questions or ideas about my tutorials. That is very welcome. Just contact me in that case. So let's go on. So first, some background information on what you need to know in order to understand regression, because it's hard when you study it at first. And it's not because you're stupid, it might just actually be because you don't know the basics. If you don't understand these basic concepts, you will have trouble understanding regression. So if you're unsure about what variables are or how to interpret a scatterplot or what Pearson's RxY is and correlation, you need to learn that first to really be able to understand regression in the way I'm teaching it in this tutorial. Now, tutorials on these concepts can all be found in my video tutorials, and so check out my website and study up on these things if you feel unsure about them. But for now, I'm just going to assume you know what these things are, and I'm going to move on in the tutorial. These are the formulas that we're going to be working with. What we have up top here is the function for a linear curve. Now that consists of two parts. It consists of a constant, which is going to be calculated using this formula, and a beta coefficient, which is going to be calculated using this formula. Now we call this the beta 0 and this beta 1. We're going to be talking about these in more depth and just showing you them so you know what this tutorial is about. So let's start talking about what these things actually mean. To begin with, we have a scatter plot, right? So we have two variables. We have the x variable and we have the y variable. And for each observation, we've noticed that each observation has a value for the x variable and a value for the y variable. Well, maybe it's something like health and income, so that this observation has a low income and also has a low health. This observation up here has a high income, and this observation here also has a high health. So you might, and then we plotted this for all the observations in our data set. This is usually what that looks like when you do it in Excel. So you have X, Y, and you have the observations here listed on a row, and their values for the different two variables. So this is the basic data set that we are going to be working with. But now what we want to do is we want to describe this data set somehow. Now I would describe it by drawing a line, because it seems like we have a positive relationship, right? So when observations have low values for x and low values for y, and other observations also seem to have high values for x and high values for y, and that characterizes a positive relationship. If I was to draw this using a line, it would be a line pointing upwards like this one. Now this is found in our function, which consists of two different components. So this line can have a height, it can be located somewhere up down, and it can have a slope. So you can see this constant here describes how high up vertically our line is located. If our constant is down here, well, our line will be located down here. If our constant is up here, well, the line is located higher up. So that's what this constant part of the formula does. Also, this line can have different slopes. So if it may have a very steep slope, or it may have a lower slope like this one. So these two things are the two things that will vary in our function. I'm just drawing them up here for you so you can see what we're actually trying to do. What we're trying to do is we're trying to fit a line here in our scatter plot that describes our observations in a summarizing manner in a good way. Now what we're going to try to do is we're going to place this line as central as possible, and in order to do that we need to take variation into account. Now, before we move on to talk about those kind of things, we need to define what all these different components can be called, because sometimes they're called different things by different people depending on how they are being used. For example, y here, which is sometimes called a predicted value. It can also be called a dependent variable, and it can be written as f of x or y with a little hat above it. Now, the predicted value, well, that is when we have a y with a hat above it usually, which means that we're trying to make a prediction about something based on variables. Perhaps it's a prediction in the future, so we say that based on these variables that we have observed back in time, we think that they are going to be like this in the future. Well, then we're making a prediction. It's not something that exists in reality. It's just a theory, an idea we have based on data. Now, the dependent variable, well, that's true too. We say that this variable here, or our prediction, is dependent on the values of our parameters and, most importantly, of our independent variables values here, which is going to be sometimes called x. And that's why sometimes this can also be called f of x, which means that it's a function of x. Okay, so y here is a function which consists of these parts here of x, which is this variable here. The beta coefficient, meanwhile, well, sometimes you may hear of standardized beta coefficient. Don't think too much about that right now. Right now we're going to use unstandardized beta coefficients, just so you know what we're talking about in this tutorial. This is called the constant, and this is called the independent variable. Now, when we're trying to draw this line that is going to summarize our observations or summarize our relationships between our two variables here, we're going to need a place to start. We need to find a point where we know this line is going to pass through. Now, because we're trying to find, we're going to use the variation between our observations to find a center set of predictions that can be used to draw this line. We know that the center, well, that must be a point where the line passes through, and that's why we have the mean of x and the mean of y here in our formula. You can see that the point where these two cross, well, that's going to be the center of our data. We know that the regression line is going to pass through this point. So that's a really good place to start, because now we know that, well, okay, no matter what the constant is, wherever it is placed, whatever value we get for this coefficient here, we know that they're going to pass through this point. But you can see we have an infinite number of variations to these lines. It can be here, there, and you know, anywhere here. So we need to identify which one of these constants we're going to be using in our regression line, and that is going to be found also by the slope of our curve. So not only the center point where we know it's passing through, we need to find the slope of our regression curve, and that is found using the beta 1 coefficient. Now, the beta 1 coefficient consists of two different parts. It consists of the Rxy, which is the correlation between the variables, and that tells us something about the direction of our relationship. Is it a positive one or is it a negative one? And it also tells us how strong this relationship is. So I've defined it here as the magnitude of the correlation between the variables, and this is going to vary between -1 and +1. You might think that's enough. That should say something about the slope, right? How do they vary together? Well, there's another problem we have to take into account, and people often forget about it, but it's really interesting. It's about the proportional effect of a 1 unit change in x on a value of y. Why is this important? Well, I'm going to show you an example because I think that's the best way to understand it. Let's say we have two different variables. In our survey, we've had a bunch of people answer our survey, and we've asked them questions such as how old are you and how many times do you swing dance in a week? Okay, so that's our x variable, and this is our y variable. So we're saying, you know, that your age defines how many times you swing dance a week. This will vary between 18 years and 97 years. So we had one 18-year-old person who answered the survey and one 97-year-old person. So it varies between these two values here. Meanwhile, how many times do you swing dance a week? Well, the lowest number of swing dances per week was 0, and the highest numbers was 10. So you can see the scales here are different. So how much is 1 year worth in terms of number of swing dances per week? That is what we need to find out. So what we do is we take the standard deviation of x first, which is found to be 19, so it varies between 25 and 63. This is where most of our people are located, and it's centered around our mean of 44. So 44 with a standard deviation of 19, we have the standard deviation of 19 there. And we do the same thing for the number of swing dances a week, so we get most of people dance between 3 and 7 times a week, around the mean of 5 with a standard deviation of 2. So we have very different degrees of variation here. You can see here that we have 19 units of variation in this variable, and only 2 units of variation in this variable. So they're obviously on different scales, so that's probably the reason why we have this situation. We need to take this into account. So what we're going to do is we are going to express our beta coefficient in terms of our dependent variable. In order to do that, what we do is we take the standard deviation of y, which is equal to 2. See here, it's equal to 2. We place that there. The standard deviation of x, which we can find here, it's 19, so we place 19 here, and that is equal to 0.11. Now what this means is that 1 year is worth 0.11 swing dances. So if we do this for our example, it's the same thing, except now these two lines are, the y line is placed there and the x line is there. So we call this the y-axis, and the x-axis is placed there. Same situation, we have the mean for y here, the mean for x here, and their standard deviations, which I have marked out in colors here. So the standard deviation for y, in our case, I've calculated that for us, is 2.74, which, okay, so it's minus 2.74 there, plus 2.74 there. And the standard deviation for x is 2.83, so slightly larger standard deviation in x than in y. So we have our x mean here, and this is minus 2.83 from distance from the mean, and this point here is plus 2.83 standard deviations from the mean, and we divide this by each other and we get 0.96. So 1 unit of x is worth 0.96 units of y. That's what we get in our example. Now the other component of our formula, well, that's Rxy, or Pearson's Rxy. Now this is a tutorial about this, so I'm not going to go into depth about it, but this is basically what we're doing. We're looking at the quadrants, and we're trying to find the distances each observation has to the respective means of that variable that we're trying to measure. So this person's distance to the y mean, this person's distance to the x mean, and the more distances we have here in the positive quadrants, the more positive our correlation is. You can see that if you added up all these distances here that these observations had in these two quadrants and compared them to the distances we have here in the negative quadrants, we seem to have a positive relationship. And if you look at it with your eyes, it seems like, yes, we see, if we were to draw a line, it would definitely be upward sloping like this, a summarizing line of it all. So the terms that we're then using, we call these the beta coefficient usually. That sounds closer to the constant, you know, the beta 0, but it can therefore also call it beta 1, which is why it's indexed with a 1 there. Pearson's Rxy, which is our correlation coefficient, it tells us something about how our variables vary together. And then the standard deviations of the independent, which is why we index it with an x, and the dependent variables. So that's the different terms that we're going to use in our beta 1 coefficient. So if we remember the original problem was that we had found the center point of our data using our means. Okay, so we had a center point. We know that the regression line is going to pass through this point, but we don't know the slope of the curve, which is what we need in order to calculate the constant, which is what we're looking for here. We want to know where this regression curve passes through the y-axis, i.e. where what value y this regression curve will have when x is 0. Well, I kind of think of it as a compass. So what we do is we find the center point of our data using these means here. Then we take our beta 1 coefficient, which is a compass, except it doesn't point north, it points at our constant. So that's what this part does. We place our compass right here in the center of the data, and it points using the correlation between the variables directly at the constant. And if I draw these little lines here, you can see that this is going to be the regression line. So it starts at the constant and goes through our center point, and we know at what slope that line it does this using the correlation between the variables and the unit relations between their axes. So now we're actually ready to make our predictions. We have our formula. I've put in our values here for our examples. We had a constant of 1.68 and a beta coefficient of 0.85. So our regression curve is going to cross the y-axis when x is 0 at the point 1.68 for y. Because if x is 0 here, this will become 0 and y will simply become 1.68. So that's how you know this is the constant. And it will do this at a slope of 0.85. So if we just put in some values here, so when x is equal to 1 here, 1 times 0.85 plus 1.68 is 2.53. So when x is equal to 1, right there, y is equal to 2.53. I do the same thing here when x is equal to 2. I go up here, x is equal to 2. And then y plus 1.68, you know, plus 0.85 times 2, we get 3.38. So go up there, and I plot my line like this, forming a regression curve that has a positive slope. I do this for all my observations. I've done this here for my example, and we get a regression curve that looks something like this. It's kind of similar to the one I just did by hand, but this time we have actually used the variation between the variables. We've used maths, we've used statistics to find a way that isn't arbitrary of how this line slopes. It's not just based on my visual interpretation, it's actually based on measurements of where these observations are located in these two variables. So that's how you calculate a regression curve. I hope you had some fun doing this. Check out the exercise tutorial, and you can, play around with this formula and see what happens when you put in different values of these. That's how you learn about regression. So if you're unclear about how this works for now, don't worry, you are going to learn it by doing it. So that is my advice to you as we move on. I hope you have a really great day, and I'll see you in the next tutorial. Bye bye.